This video I'm going to give you an idea about basis of a graph, basis vectors of a graph and subspaces in the vector space of a graph. In general, if every vector in a vector space, say W, can be expressed as a linear combination of given set of vectors, then this set is said to span the vector space W. Okay, and the minimum number of linearly independent vectors which spans the set is that gives you the dimension of the basis. If I say any set of vectors, say v1, v2 like that, vn, this set of vectors form a basis for a vector space, say W, if the condition is, first one is these vectors v1, v2, vn, they have to be linearly independent and they should span the vector space W. If every vector in a vector space W can be expressed as a linear combination of given set of vectors, then that set of vectors we call it as they set to span the vector space. Okay. So dimension of the vector space W is the minimum number of linearly independent vectors that require to span W. Okay. Now remember one thing, a vector space can have any number of bases, but the number of vectors in each of them must be equal. Okay, and the number of elements in the basis we call it as dimension of the vector space. So if I have n number of vectors in my basis, then if I consider any n plus 1 vectors, then they are linearly dependent. Okay, if I have n dimensional vector space, then any n plus 1 vectors are linearly dependent. Okay, now vector space, basis for a graph, basis vectors of a graph. We know that with each graph G, there is associated vector space. I'll denote it as WG. Okay. Now corresponding to each subgraph of G, there was a vector space, there was a vector in WG represented by E tuple. Okay, that we have seen in last video. So to each subgraph of G, there is a vector in WG which is represented by E tuple, or depends on how many edges it has got, E tuple. The natural basis for this vector space WG is a set of E linearly independent vectors, each representing a subgraph consisting of one edge of G. For instance, if I have a graph like this, okay, if this is my graph, I have an edge E1, E2, E3, E4 and E5. Now for the above graph, I have following these 5 vectors which forms a vector space WG, forms a basis for the vector space WG. That is, see, first one E tuple. So there are 5 edges. If I consider only this subgraph, 1, 0, 0, 0, 1, 2, 3, 4, 5. Okay, like that if I have only edge E2, like that if I have only edge E3, only E4, only E5, they form a basis, the natural basis for the vector space WG. See, These are the vectors which forms a basis for WG. In fact, any of the 32 possible subgraphs, including the graph and the null graph. Of course, we know that there are 2 to the power 5 subgraphs. Okay. So any subgraph including graph as well as the null graph can be represented uniquely by the linear combination of these vectors. Okay, that's why we say that this forms a basis for the vector space WG. Next comes subspace. A non-empty subset of a vectors in a vector space is said to form a subspace if that subset satisfies the axioms of vector space. Okay, and every vector space is a subspace of itself, and the set containing null element, thus alone, this is also a subspace, and the dimension of a subspace is a number of linearly independent vectors which is required to span the subspace. These are basic ideas about subspace. Subspaces in WG. In the vector space WG over the Galois field modulo 2 associated with the graph G, we are considering two types of vectors. One is a circuit vector. It's a vector in WG, circuit vector. It's a vector in WG representing either a circuit or an union of edge disjoint circuits in graph G. And another one is a cut set vector. It's in WG, it represents either a cut set or an edge disjoint union of cut sets in graph G. We know that in vector space WG, the linear combination of two vectors corresponds to the ring sum of the corresponding subgraphs in G. So that we have studied. So the ring sum of two circuits is a circuit or union of edge disjoint circuit. Therefore, the linear combination of two circuit vector is also a circuit vector. Hence, we are going to prove a theorem that says the set of all circuit vectors in WG forms a subspace W gamma. See, I have mentioned already how we are proving that. Just I'll explain once again. W gamma, I'll take it as set of all circuit vectors. Okay, this is set of all circuit vectors in WG. Now we know that in the vector space WG, the linear combination of two vectors corresponds to ring sum of corresponding subgraphs in G, that we have done already. But the ring sum of two circuit is either a circuit or an edge disjoint union of circuit. Hence, the linear combination of two vectors, if I consider, is also a circuit vector, and hence it is in W gamma. That's what the proof is. Set of all circuit vectors in WG forms a subspace. Based on the similar arguments, you can even prove that set of all cut set vectors in WG form a subspace, say W. Yes, that is cut set subspace. Okay, this is circuit subspace and this is cut set subspace. So same manner we are proving set of all cut set vectors in WG form a subspace WS. We are going to prove one more important result, that is the set of circuit vectors corresponding to the set of fundamental circuits with respect to any spanning tree forms a basis for the circuit subspace W gamma. Okay, I have to take all the fundamental circuits. I have to take a set of fundamental circuits, okay, with respect to any particular spanning tree. I have to show that they form a basis for the circuit subspace. To show basis, first I have to show these fundamental circuit vectors, they are linearly independent, and next I have to show that they span the subspace W gamma. So first part is proving the fundamental circuit vectors are linearly independent. For that, first initially I'll consider a spanning tree T. Let T be a spanning tree with say T of a connected graph G, with say R equal to n minus 1 branches and E minus n plus 1 chords. They are nothing but the rank and nullity. That's okay, no problem. I'm considering R branches and mu chords. Now, I know fundamental circuit is obtained by adding a chord to a spanning tree. Now, I'll add this C1, chord C1 to the spanning tree T. Okay, and it produces a fundamental circuit and the corresponding circuit vector. And that corresponding circuit vector I'm including in W gamma. Okay, W gamma, that's a subspace. I'm adding a chord C1 to the spanning tree and it produces a fundamental circuit, hence it produces a corresponding circuit vector, and that circuit vector, say some C1 vector, okay, that vector I'm including in W gamma. Okay, now I'll add one more C2 to the spanning tree T. In fact, not the spanning tree only, I'm adding this to the previous graph. Okay, initially I have added C1 to the spanning tree, so I got a circuit, one fundamental circuit I have already got. In that, for that I am adding one more chord. Okay, it produces one more circuit vector. Okay, this addition of this C2, C1 already it is there, and I'm adding C2, and this C2 that produces one more circuit vector, and then that I'm taking in W gamma. Okay, which this circuit is not found in the previous case. Once I have added one chord, I'm getting only one fundamental circuit, and I'm adding second chord, I'm getting one more fundamental circuit. Okay, that circuit has got at least one edge extra, which was not there in earlier case. Okay, so I can say the circuit vector representing the second fundamental circuit and the first circuit vectors, they are linearly independent because they have at least one edge which is not common. Okay, thus I can say these two fundamental circuit vectors, they are linearly independent, and this can be added to the basis. Now I am adding third chord. I'll add one more third chord. Will give another fundamental circuit with at least one edge which was not found in the previous circuit. Therefore, the third circuit vector can also be added in the basis. Continuing this process, see how many chords are there. I have got mu chords. So continue this process. We see that all these mu vectors, I'm getting mu vectors, they are linearly independent because each represent a circuit containing at least one edge which was not found in the previous vector. So I'm getting mu vectors, which are linearly independent. Each vector I'm getting by adding mu chords. Okay, now I have got mu vectors which are linearly independent, and each vector represent a fundamental circuit. So first part is over, that is showing set of vectors, set of fundamental circuit vectors are linearly independent. Now I have to show that every fundamental circuit vector is a linear combination of these mu vectors. I mean, I have to show every circuit vector is a linear combination of these mu vectors. For that, I'll consider an arbitrary circuit. Okay. I'll consider an arbitrary cycle, so it is denoted by gamma 1 in my graph G. Okay, in such a way that it has got, say, I'll write it E1, E2 dash dash, EI plus 1 dash dash, say EM. This is just notation, okay, where this E1, E2, EI up to EI are the chords with respect to T3, spanning tree T, and these are the branches. I'm just naming it as E1 up to EM. They are the edges of this arbitrary circuit gamma 1, and in among those edges E1 to EI are chords, and EI plus 1 from EI plus 1 to EM are the branches. Now I'm taking a subgraph. Say let G be a subgraph. G be a subgraph obtained by taking the ring sum of I fundamental circuits which are formed by these chords. Okay, the G be a subgraph which is obtained by taking the ring sum of I fundamental circuits formed by these chords. See, this is my arbitrary circuit and they have got these chords. Now what I do is I'll define one more subgraph in such a way that each time adding these E1, E2, EI chords, I'm getting a fundamental circuit, and I'm taking ring sum of all those I fundamental circuits, and I'm calling that as a graph G, which is a subgraph of G in fact. Okay. Now I know that ring sum of circuit is again a circuit or a edge disjoint union of circuit. Therefore, this subgraph G must be a circuit or an edge disjoint union of circuit. Okay, it must be G must be a circuit or an edge disjoint union of circuits. Because of the theorem which we have proved already, ring sum of any circuits is a circuit or an edge disjoint union of circuits. So when I get this G, in fact this arbitrary circuit gamma 1 and this G are equal. I'm claiming that this gamma 1 is equal to G. This is what I claim. How? Let us see that. Suppose if these two are not equal, what happens? I'll assume the contradiction part. That is, suppose gamma 1 is not equal to G. Okay. Then the subgraph I'm taking a subgraph which is, let the subgraph is obtained by gamma 1 ring sum G. Then since this is an arbitrary circuit and this is a ring sum of fundamental circuits, so this is again a circuit or an edge disjoint union of circuit. So circuit and the circuit, I'm taking a ring sum. So this must be a circuit or an edge disjoint union of circuit. This ring sum since this is also a circuit or a ring sum of circuit, and this is already a circuit, this ring sum is a circuit or an edge disjoint union of circuit. But we know that the chords which I am considering, E1, E2, EI, they are both in G and in gamma 1. These are the chords with respect to spanning tree T, and they are in both G and gamma 1. Therefore, when I take the ring sum, they won't be there in this ring sum. This ring sum should not contain these edges. Okay. Therefore, I can say that this gamma 1 ring sum G will not contain any chord with respect to T, spanning tree T. Hence, I can say that this has no circuits. This has no circuits, which is a contradiction to the fact that since G is a circuit or a edge disjoint union of circuit, and this is a circuit, so their ring sum is also circuit. So that gives the contradiction. Okay, hence gamma 1 should be equal to G. Okay, thus we have shown now that any circuit in G can be expressed as a ring sum of any circuit in G can be expressed as a ring sum of fundamental circuits with respect to particular spanning tree, say T. Therefore, I can say that vectors corresponding to a set of fundamental circuits, they span W gamma. We have already proved that they are linearly independent, and now I am proving that the vectors corresponding to fundamental circuits, they span W gamma. Therefore, I can say that mu circuit vectors form a basis for the subspace W gamma. Corollary to this theorem is the dimension of a circuit subspace. Okay, if I take the dimension of circuit subspace is equal to nullity of a graph, that is mu, and the number of circuit vectors in W gamma, number of circuit vectors in W gamma is equal to 2 to the power mu. In the similar way, I can even prove the set of cut set vector corresponding to the fundamental cut sets with respect to any spanning tree. They form a basis for the cut set subspace. Okay, and for the same manner, the dimension of cut set subspace, which is equal to rank, and the number of cut set vectors is equal to 2 to the power r. Dimension of cut set subspace is equal to rank, and number of cut set vectors in Ws, which is equal to 2 to the power r. Next is orthogonal subspaces. We know what is orthogonal vectors. Two vectors are said to be orthogonal if their dot product is 0. And I can say the dot product of two vectors x, y, if I have two vectors x and y in a vector space W, it's a scalar quantity which is defined as, say, dot product I am considering x dot y. It's a scalar quantity, that is x1 comma x2 dash dash xn dot y1 comma y2 dash dash, say yn. Then this is nothing but x1 dot y1 plus x2 dot y2, like that, xn dot yn. Okay, this is dot product of two vectors x, y in a vector space, say W. I am defining orthogonal subspaces, okay, two subspaces are said to be orthogonal to each other if every vector in one is orthogonal to every vector in the other. Then I can say that two subspaces are orthogonal. Just to explain the orthogonality of vectors, suppose I have graph G. Suppose this is my graph G. Say I'm taking same example, almost same example to explain one full topic, so that with an example you can remember the properties or things associated with that graph. So I'm taking same example every time. So this is my graph G, and G1 and G2 are the subgraphs of G, and this is the vector representing this subgraph, and this is the vector representing this subgraph G2. Now if I take their dot product, 1 into 0 is 0, 0 into 1 0, 1 into 1 comes 1, and then again 0 0, so the value you are going to get is 1. See, the number of non-zero entries in the sum of products above, that gives me the number of edges in common between G1 and G2. When I consider G1 and G2, only one edge is common. So this dot product gives me what are the number of edges in common between the subgraphs. In fact, there is a theorem which states the dot product of two vectors, one corresponding to the subgraph G and G dash, if that product is 0, dot product is 0, if the number of edges common to G and G dash is even. If number of common edges is even, then dot product is 0. Dot product is 0. If number of common edges is odd, then the dot product is 1. In this case, number of common edges is 1, therefore the dot product is 1. So we say two subspaces are orthogonal to each other if every vector in one is orthogonal to every vector in another. Now, in fact, the circuit subspace and the cut set subspace, they are orthogonal to each other. So let us prove that. We know that the number of edges common to a circuit and a cut set is always even. And I can even say number of edges in common to a union of edge disjoint cut set is also even. For that, say I can first argument is very easy if I have simply circuit and cut set. They share a even number of edges. But if I have edge disjoint union of circuits, then what happens? Will they have same number of edges in common? Sorry, even number of edges in common. Say suppose I have G1, it's a edge disjoint union of circuits, say gamma 1, gamma 2 and suppose gamma 3 of graph G. Okay, this is a edge disjoint union of this circuits. And G2, this is a circuit, okay, and G2 is a edge disjoint union of cut sets, say S1 and S2. Okay, suppose if I have a graph G, then the G1 is an edge disjoint union of circuits and G2 is an edge disjoint union of cut sets. Now, the number of edges in common between gamma 1 and S1 is even, because gamma 1 is a circuit and S1 is a cut set, so this is even. Similarly, if I consider gamma 1 with S2, that is also even. Sorry, S2. Similarly, if I take gamma 2 with S1, gamma 2 with S2, similarly gamma 3 with S1, gamma 3 with S2 every time when I consider a circuit and a cut set, I know they have even number of edges. So this is true for all the circuit with these cut sets. Since there is no edge common between S1 and S2 or between gamma 1 and gamma 2 and gamma 3, this six sets of common edges enumerated above are all distinct in fact. Therefore, I can say the number of edges common to G1 and G2 is this plus this plus this plus this plus this, which gives me an even number in fact. So, the number of edges in common to a edge disjoint union of cut sets and edge disjoint union of circuit is also even. Therefore, I can say that the dot product of circuit vector dot cut set vector is equal to 0 because of the previous theorem which I mentioned. If dot product is 0, that means number of common edges between two subgraphs is even. If the dot product is 1, then the number of common edges between them is odd. Okay. So now I have got dot product is equal to 0. Hence, every vector in this circuit vector I am considering. So every vector in each of these subspaces, W gamma and Ws, they are orthogonal. Therefore, I can say that the circuit subspace and the cut set subspace, they are orthogonal to each other.